It's an unfortunate fact about many applications of solving linear equations that often the matrix that shows up has many, many more rows than columns. And in that case, usually the system of equations is going to be inconsistent. But you'd still like to have something as close as possible to a solution. So what can we do in that case? Well, remember, another way to think about what's happening here is that x lives in some domain space, right? So there's this domain space of, it's a vector space, and a multiplying by a is a linear transformation that transports you to some other vector space. So I'm going to draw it as if it's R3 over here. And so multiplying by a sort of situates your domain space in the range space somehow, right, like this. But this vector b, it might not actually be, right, if this is b, our vector b isn't in the image of a. So there is no solution in this case, right? You can see whenever the dimension of the range space is larger than the dimension of the domain space, then most choices for b will make this equation inconsistent. And that's exactly the situation when a has more rows than columns. So, but what we like in this case is some vector over here in the domain, so that when you hit it with a, it gets as close as possible to b. So we can't produce b exactly, but b casts this shadow down on the image of a. This plane is supposed to be depicting the image of a. And there is some, since this is in the image of a, there's some vector over here as close as possible to b, some vector in the image of a as close as possible to b that we can hit by starting over here. So there's this vector, I don't know, let's call it y, over here that's close to b, and then there's some vector that hits y. So there's sort of a two-stage process here, right? First, we're going to need to find this closest vector y, and then once we know the closest vector y that's actually in the image of a, then we'll find the x value that hits that y. So that's our strategy for solving this sort of inconsistent system, and this is usually called a least squares solution because this situation is going to minimize the distance between ax, right? Y is really ax if we can find x. Y is ax. So this situation is going to minimize the square of the distance between ax and b, and so that's why it's called least squares. So our strategy for solving this for finding a least squares solution is, first we need to find the vector y in the image of our matrix A that's the closest to b. And then once we know that y, then we will replace b with y in this equation. Now this equation is guaranteed to be consistent because we know ahead of time that y is in the image of A. So that means that this is consistent. Then we can just solve this system. So that's the general idea. You see, we have this sort of two-step process, and we'll take these a step at a time because it turns out neither one of these steps is exactly easy.